Now that we've made an initial sketch and we can see some of the key features that our output is going to have, we're going to add a little bit more detail to it so that we can get a better quality sketch with the proper peaks and valleys and timing of where these oscillations are happening. So first we need to look at the attenuation in our system. All right, so again, we're only looking at stable underdamped systems right now. We see that they oscillate around that steady state value and they're going to gradually lose energy. And the bound of these oscillations is going to have an exponential decay. Again, if we look in the time domain solution, we're going to have an exponential times a sine and a cosine. So that exponential is causing the overall oscillations to get smaller and smaller as time goes on. And the system is going to oscillate not at the natural frequency, but at the damped frequency. A common misconception is that things are going to always oscillate at that natural frequency because that's what you saw in like your physics 1 course. But really that was happening because the systems you looked at were undamped. So in that case, yes, it did oscillate at the natural frequency. But that was only due to not having any damping. All right, so let's see what's the frequency of response in these damped systems. So like I just said, they're going to be oscillating with an angular frequency of omega d. But we can go from our angular frequency to our period of oscillation by just converting between our angular frequency and our period. So the period of oscillation, the time between peaks, the time between valleys, is going to be 2 pi over omega d. And actually, if we think back to peak time, we found that that was pi over omega d. So really what we were finding there is that the peak is going to happen at half a period, and then we're going to see our first trough, our first valley, at 1 full period. So again, this capital T is the time between two peaks, any two subsequent peaks or any two subsequent valleys. Right, so peaks are going to happen on the half periods, and troughs or valleys are going to happen on the whole periods. Right, and those oscillations, again, are going to get smaller every period, and in fact, as time goes on, they'll just get smaller. So we're going to be able to bound these oscillations above and below by using this equation. So these will be y here is not the value of our response. Y here is just some bounding curve that we're going to see what it looks like in our example. So we're going to take the steady state value and multiply it by 1 plus or minus this exponential term. And what we're going to see is that when we do 1 plus the exponential term, we're going to get a curve that is above our oscillations. And when we take the minus, we're going to see a curve that is below our oscillations. One thing we can do to find what the value of a subsequent peak or a subsequent valley is going to be is by using the ratio of our peak values, using this relationship here. I don't have it highlighted. I'm not going to discuss it too much because I think it's a little bit overly complicated to use. However, it is useful when we have experimental data, so I do want to present it here. But I want to go back a second to the highlighted equation that we have. So again, this is not the response of the solution to the response of our system exactly. It is just that bounding curve. However, the way we can use this is this equation, the bounding curve intersects our response at all of the peaks and at all of the valleys. So one way we can use the highlighted equation here is to find the value at whatever peak we want, because we know the time when peaks occur. Peaks are occurring at half of a period, 3 halves of a period, 5 halves of a period. Every half period, we're going to see a peak. So if we put that time that we found on the previous slide, those times in for t in the highlighted equation, that will give us the value of our response at that peak. If we're looking for valleys or troughs, well, those are happening at whole periods. So if we put in capital T or any integer multiple of it, we can find the value of our response at that time by putting it into little t in this highlighted equation. And then, yes, the value of the bounding function is equal to the value of our response only at those specific times. We'll see how do we use this a little bit more in the forthcoming example.